All right, welcome to Makeup Week for Computer Organization and Architecture. We will be covering basically chapters 9, 10, and 11. And from there, we will pick up and cover chapter 12 in class. So basically, these upcoming chapters are important for you to understand just as a background to where we're going to go from here. All of this content is directly from Douglas Commer. I modified a couple things, but most of the content is from 2009, just with a few modifications by myself. So as far as memory goes, memory is divided into, well, first of all, actually, back up a step. Um, there's all kinds of different types of memory. We usually think about the main memory that's holding a program that's running and any data that that particular program is using, but you can also think of memory in a broader sense. And usually when an architect is looking at memory, they're thinking of the actual device that provides storage for values. So it's more of a low-level definition of memory that we're actually talking about here. And basically when an architect goes to design memory, he or she is going to divide memory into two key choices that need to be made when creating memory. The first choice is the technology, and that's whatever underlying hardware mechanism is going to be used to construct the memory. The second key choice is organization, and that's exactly how the memory is organized. So what size of units, how many bits and bytes are in each unit, how the units are organized together in terms of layers. All of that can become topics of organization and design characteristics that have to be figured out. So as far as memory characteristics go, there's volatile or non-volatile memory, basically referring to whether or not it can be changed. There's random or sequential access, referring to the order in which data must be read. So random access means that it can be read, any value can be read at any given time. But with sequential access, even if you want to read a value, you have to read all the values prior to it. It's basically you're reading from memory in the order that was inserted at. And read or write only, read only or write only, read write or write only. All of those are different types of characterizations of if memory can actually be read from and written to at the same time or only read from. So read-only memories refers to ROM because that's memory that has data values that can be accessed, but they can't actually be changed. So we'll see that ROM becomes useful in many cases for things like BIOS and other types of hard solid state sort of things that never need to be changed. They're set once, maybe at the manufacturer or something like that, and then never changed again. That's especially true for programmable read-only memory, where you basically program it first, and then you never plan on changing it ever again. Use some physical circuits on the chip to do this, and you burn that in essentially, and then that can be accessed many times. And reasons why you would use these are usually that it's faster to access them. Electrically erasable programmable read-only memory is another thing that's popular. As I mentioned, there are many current variations of this. One would be flash memory or flash ROM that you see. It's kind of ubiquitous now. You see it all over the place. So those are all various types of read-write or read-only memories. Primary or secondary refers to if the it's kind of a qualitative description, um, and now it's sort of two distinct solid-state technologies. Um, so small portable devices have microdrives, and these are used to store files. So basically, it's evolved over time from distinguishing between fast, volatile internal memory and non-volatile storage. So for looking at this in a little bit more depth, volatile memory is when the contents will disappear if the power is removed. So this is like your average RAM that you might think about existing in a computer, like if you have 4 gigabytes of RAM or whatnot, or 8 gigs. That is the runtime memory that's in the computer, and that's going to disappear. The non-volatile is usually what we think of that remains on without power. So, for example, hard drives. These usually have slower access times, which is sort of why virtual memory ends up being slower, because it has to go through the non-volatile memory in order to access it. Um, as I mentioned, random access is typical for most applications as far as a paradigm. In read-only memory, this, as I mentioned, this would be useful for like BIOS, like firmware or something like that. These can be read but not changed. Changes in programmable read-only memory may involve removal from a circuit and exposure to ultraviolet light. So this can be altered, but it's pretty time-consuming to do so. And then EEPROM, so flash ROM, is something that is very popular today. So with primary memory, if we go into the details like I was mentioning before, this is the highest speed memory. It's usually solid-state technology. It's expensive, but it's the smallest piece. So usually when you're thinking about this, you're thinking about a memory hierarchy, and we'll get into this in a little bit. As you could see there, I just flashed forward, but it's sort of you want sort of a hierarchy to exist between the memories that you're using. The primary memory being the fastest, the most expensive. So similar to your cache, for example, and that doesn't have to be considered a cache. This is an important distinction. Primary memory you could use in the same sense that we use RAM, but that would be very expensive, and also not really proven to necessarily be any benefit, because once you have everything as primary memory at the highest speed setting, then it's hard to be swapping in and out whatever is most important at any given time. In other words, your cache, as we'll see later, needs to be a certain size. If you just have a ton of things in your cache, you end up having to search through all those things when you're paging. Whereas if you have a primary memory and you use that as your cache and you're searching through things, there's a small amount of things that are going to be known to be hit time and time again. So a good example would be if you think about a typical loop that you're coding up in Java or something like that. The memory that occupies the space during the loop, like say a for loop or something, and in that loop is going to be accessed many times over and over. But stuff outside of the loop may or may not be accessed. So it's kind of up to the designer whether or not some of those things go out to secondary memory or they still sit in primary memory. Now, secondary memory, on the other hand, is lower speed. It's less expensive. It's larger. And usually this means that it's used in a secondary nature, and we can have more of it. So there is this idea that, for example, memory cards being used in digital cameras or flash um, being used, flash drives being used on laptop computers. Technically, that's basically a EEPROM kind of setup. So it's kind of a blurry line between whether that's actually primary or secondary because it's being used in a secondary nature. It's storing stuff, but yet it's primary memory in the sense that the distinction of what primary memory is, the highest speed, most expensive, therefore smallest, it really technically is primary memory, but it's being used in a secondary memory nature. Also, solid-state hard drives being used in laptop computers these days, and well, basically all types of computers, are evidence that what we used to think of as primary memory devices and being used just things like cache are no longer the case, and now those are being used in a secondary storage nature. So it's very important, as I mentioned, to think about the memory hierarchy. We have to consider performance and cost of memory. So it's research on all of this has led to something that's kind of an interesting find, as I mentioned. It's not actually optimal to use one type of memory throughout a computer. Instead, what designers usually want to do is they want to organize it into a memory hierarchy. So you would have a small amount of the high performance memory, slightly larger amount of slower memory, and so on. The idea here is that if you have everything in the fastest, highest speed memory, it would technically be a small speed up to have everything, say, in what we used to consider as primary, the solid state type stuff. But you're going to reach a plateau that occurs because no matter what, you need a lookup table to get to those entries in your secondary or tertiary storage. So as I said, you basically want a set of technologies and you want to arrange them in a nature that's suitable for you. And that's, I've already alluded to, like the idea of caches and versus RAM versus solid state hard drives, but these are basically trade-offs that you have to make, and your highest performance memory is going to be in your cache, and that's going to be the one that costs the most. And the architect needs to choose which one of those are at which level within the memory hierarchy. So here's an example hierarchy. We'd have a dozen or so general purpose registers stored on the chip, and then 1 to 2 gigabytes of main memory. And this actually doesn't talk about the cache either. The cache would kind of be sitting somewhere between these two. And then, hundreds of gigabytes or even a terabyte of secondary storage. So notice that the old definition of primary storage being just for the registers, just for the cache, secondary being for just for the storage. Now with solid state drives, you can really think of that as primary, but yet with the definition of secondary. So as we mentioned on that previous slide, it's become a pretty blurry line between secondary and primary. So as far as computer memory goes, it's typical to have separate memories, one for programs and one for data. Or another typical way of doing it is having a single memory that holds both the programs and the data. Some of the earliest ones that were invented from the von Neumann architecture use separate memories for programs and data, but then later on it ended up combining into single memory holding both programs and data. And even today, there are some that still do it the first way, but over time, it became easier to store everything in a single memory that held both. And that's why when you see coding in assembly, which we're doing now, as you know, the data section is basically just a separate section above the program logic. And as you can imagine, that's stored right next to each other in memory. In fact, you can look at that in memory in EBE and stuff like that, and you can see that they're right next to each other. So it's being stored in this place. And as you've traced through sort of your von Neumann machines, as we did on the exam and things like that, the program counter will go line by line through the memory. So a single memory design is really sort of synonymous with the von Neumann architecture. So in this architecture, we have instructions and data occupying the same memory. So let's consider for a second this following C code. Here's a short main, which is basically just an array of shorts. The question is, does this specify instructions or data? So that answer is kind of dependent upon how this code is being parsed. Now, clearly, all of these are values inside this big array called main. But there is an assignment instruction there with the equal sign. There is an assignment with a declaration of the type of memory right before the main word here. So this keyword short and then main. So it's actually occupying both. And typically, this is all in the C code. And so you don't have to think about, oh, well, this, if we didn't do it that way, you would have to think about all the memory that's declared here and what their values are separate from this assignment. And then one would have to go in each area of memory. But because of the von Neumann architecture, we don't really have to worry about that. So there's some special purpose processors that might require separate instructions and data stores. These are sometimes evident in things like GPU processing and a couple other types of processing. There is the existence of separate caches that we'll talk about, the L1, L2, L3. And this allows for that hierarchy that we talked about to really optimize the best use pattern. Access patterns on these types of things typically sequential if it's an instruction store, or random if it's a data store. We've already talked about the idea of fetch execute cycles, but here's the fetch store paradigm. These are the two basic operations associated with the paradigm we're talking about. So the idea is you fetch a value from a specified location, you store it to a specified location. And when we're doing our move operations in assembly, that's the same kind of thing. Move does a store, but we can also do a fetch inside of it to get the original value on one of the operands and store it in another operand. So those are the main things under the assembly code that we're doing that need to be carried out on memory. These are also called read and write. So when you do a move command from one thing to another, you're reading it from that original position and putting it in the destination, writing it to that destination. So in summary, this was kind of a generalized chapter, chapter 9, and we've looked at some of the technology aspects of these design choices in organization, and primary versus secondary memory, as well as random access versus sequential, and a few other topics. So we will go on next time to cover chapter 10. All right, see you soon. This is the beginning of chapter 10 here, and this is where we'll pick up from next time, or for next time rather.